Welcome to the first module of the Ethereum Bootcamp. In this module, we'll be diving into concepts from Ethereum, Ethereum 101. But before I dive in, I want to step back and provide the context for the format that we're going to use in all the modules of this bootcamp. All these modules, the content that that's going to be shared with you, the videos will be following what is known as a checklist-based approach. This is something that I've written about, talked about. This essentially means that all these concepts will be provided in an itemized manner. So when we say Ethereum 101, we are really talking about a checklist of 101 concepts provided in in an itemized format, right? So we'll be talking about each of those concepts, and this checklist-based approach has many advantages. It's easy to refer to, it's easy to discuss. It's also known to be very conducive to remembering and recollecting. So that is something that you will see repeatedly across all the content that we're going to be using in this bootcamp. I also wanted to set the expectations for the content. This is something that you will see during the bootcamp. Is we have a lot of ground to cover, be it Ethereum, be it Solidity, be it security, be it auditing. We are looking at research and best practices that have been brought together over decades. Ethereum has been researched and developed over the last 8+ years. And then when you look at Solidity, it's the same thing. Security and auditing span decades of work. So it's really not going to be practical to deep dive into each of those concepts during these videos or in the content provided. But there will be a lot of references provided. So feel free to dive into the details as much as you can in your own time. But we will be discussing all this to the greatest extent possible in the various forums during the bootcamp. So that is the expectation that I wanted to level set. And this is also a bootcamp where a lot of you are coming from different backgrounds with different levels of expertise in each of these concepts. So there might be concepts that you're already familiar with. Feel free to skip them or skim them. And if there are concepts that you're not familiar with, say in cryptography or in Solidity, take your own time, spend a little more time on them, and try to make sure that you catch up to the extent possible so that you actually follow through the various concepts during the rest of the bootcamp. So with that, let's dive into Ethereum 101. So Ethereum is a blockchain, which should be obvious by now. It is if you look at the white paper, and I would strongly recommend everyone starting off to actually read the white paper that was put forth more than 7 years ago. So go through it. There are a lot of those initial concepts, the motivation, the grand vision for Ethereum written very elaborately in the white paper. And the white paper proposes Ethereum to be a next generation blockchain that supports smart contracts to allow decentralized applications to be built on that platform, right? So this is this might seem obvious by now, but if you roll back to when the white paper was written, there weren't so many blockchains available and ready to use back then. And Ethereum was really one of the first ones to put forth this idea and go into this concept of a next generation smart contract based decentralized application platform. And we'll look into each of these concepts during the rest of this module. One of the fundamental aspects of Ethereum is the fact that it is Turing complete. Ethereum supports a Turing complete programming language. And Turing completeness is a fundamental concept in computer science. So if you haven't come across it, I would encourage you to look up Wikipedia or one of any of the computer science books to see what it means. But at a high level, what it refers to is the expressiveness of a programming language, right? What is it that you can do with it? Um, is the logic that you can express with that language? Is it can it be arbitrary? Is it bounded or is it unbounded? Things like that, right? And Ethereum, like many of the high-level languages that you're familiar today, right? Be it C, C++, Java, Python, Rust, Golang, all these languages are Turing complete. So Ethereum also supports a Turing complete programming language, and therefore is expressive enough in arbitrary and unbounded ways. And this is very powerful, and we'll see how this affects the design and security aspects. So smart contracts written on Ethereum are Turing complete because of this, and these smart contracts lend themselves to decentralized applications. And what this really means is that these smart contracts and applications can really encode arbitrary rules over arbitrary states. So these states can be read and written using these rules, and this really contributes to what is known as a state transition. And if you're familiar with finite state automatons from computer science, this is what it really is, right? So you have a state, a rule is applied to that state, it reads the state and modifies the state and takes it from state to state prime. This is sort of the formalization. So this is sort of a fundamental state transition rule, and this can be done with the Turing complete programming language in arbitrary ways without any constraints on it. So any state, any rule allows Ethereum to really support any application on it without any artificial constraints coming from the programming language or the platform. The next topic that I want to touch upon is infrastructure, right? So what is the infrastructure that underlies Ethereum? At a high level, Ethereum is an open source, globally decentralized computing infrastructure, right, that executes smart contracts. Now, by design, everything in the space is open source, be it the protocol, the specification of the protocol itself, and all the code that actually implements that protocol. Everything is open source, and you will see this. With the smart contracts and the rest of the software infrastructure that is used and that's developed. Is that by design, the expectation is that everything is open source, right? So everything is transparent. This is something we'll get back to again, and this has big implications to security, as you can imagine, and we'll be covering and talking about it more later on. So it's a blockchain. Ethereum is a blockchain, and it's used to store the state, the various state from the smart contracts. It is used to store that, and given that it's a blockchain, it's decentralized. So there are many nodes that all have to agree upon and that all have to synchronize the global state, or the single view that everybody agrees on and works with, right? So that is another, that's probably the biggest part of the infrastructure, is that it is a blockchain with this global state, right? And then there is a native currency in Ethereum. It's called Ether, and it's used to meter to measure the amount of resources that is being used when smart contracts run, and it's used to constrain how long and how much resources they use up, right? And this becomes important. It ties into the Turing completeness, which we'll talk about very shortly. And all this infrastructure is what enables this vision of Ethereum being a world computer, right? And we'll talk more about this again in the next few slides. So what are the properties of Ethereum, the world computer, right? And what are all the properties that actually drive the vision and the implementation and the design of everything that really becomes part of the Ethereum infrastructure? The fundamental property that drives this vision is that of the applications being permissionless. What does that mean? What it means is that if somebody were to build any part of the infrastructure for Ethereum, if you're building the protocol, if you're building the Ethereum client, if you're building smart contracts, then anyone can really build it without permission from any centralized entity within Ethereum, right? You can build it. All the tools are open source. Everything really ties in. It's open source, so you can actually look at it. You can extend it, and you can also deploy it without anybody's permission. And you can also use it without anyone's permission, right? This is what lends to permissionless applications, decentralized applications, and contrast this with how you build, deploy, and use the mobile applications today, say on the Apple platform or the Google platform, right? Where you have a centralized entity that you have to register with, get the permission from, test with, follow the regulation, follow the policies set forth by that entity, by the Play Store or Apple Store, and then deploy it. And then there are certain ways in which you can use it as well, right? So we'll talk more about this contrast between Ethereum or broadly the Web3 space and the current existing Web 2 space, and this is a key aspect of permissionless interaction, development, innovation, right? And all this really happens, really is incentivized because of the built-in economics. And this is something we'll get back to again, talk a little more deeply about. But this is what is commonly referred to as crypto economics. So this incentivizes people to run the Ethereum nodes, to deploy applications, to use the applications. All this incentivization is really what is very key to Ethereum and to Web3 in general. The other properties are that of high availability and high auditability. High availability refers to the fact that Ethereum is always up and running. It's 24/7, 365 days of the year. There's never really a downtime that is expected because of upgrades or because of any issues. I mean, that's the goal. And again, contrast this with some of the other services that you work with, where they might be taken down for maintenance, for upgrades, or any other reasons, right? This is a key property of decentralized infrastructure, right? And the fact that it is decentralized enables the infrastructure to have this high availability because there are no centralized infrastructure choke points, right, that can go down and bring the whole infrastructure down, right? So that is by design something that decentralized infrastructure makes available, right? High auditability really refers to the fact that everything that happens on Ethereum, everything that happens on the blockchain is auditable. And by auditable, we mean they can be examined, they can be analyzed, and reasoned about. This lends itself to high degree of transparency, right? So there's, by design, everything is meant to be very transparent, be it the source code, be it the design of the protocols, be it the transactions that interact with it. So nothing is meant to be proprietary and behind paywalls, or in a way that you really cannot reason about the security or the transparency aspects of it. That's at least the high level design goal, right? And all these properties really lend itself, make the platform, make everything that's built on the platform highly neutral, and we'll see more about this as to how decentralization really contributes to this neutrality, because there's really no centralized entity that can change the availability, auditability, or transparency aspects of the platform or applications built on top of it, right? So that's these are some of the key properties, and all these again lend itself to a very high degree of censorship resistance. Yeah, and this is again something you're familiar with, in existing platforms. If an app or a website or anything else does not subscribe itself to the compliance aspects of the platform or any other entity, then it might be deplatformed, right? It can be taken away from the platform at any time by the entity that is controlling that platform. And there are many stories of this, being done extremely wrong. There have been accidents where unintentionally some of these apps were taken down because they fit into some larger category of app or type of applications that were being deplatformed or that were being removed from the platform. So there are many aspects of this from a censorship perspective, and Ethereum and decentralized applications, blockchains in general, make this hard to do, very hard to do at a platform level, right? So this property of censorship resistance is again a very critical one, and then some of the applications, let's say the financial ones, this leads to what is known as lowering the counterparty risk. The party that you're interacting with, be it the platform, be it the application on top of it, or the logic, there is always a risk that is associated with it. And because of these properties of transparency, neutrality, censorship resistance, that risk is much, much lower. So none of this is black or white. They're all on a spectrum, and we're really progressing. We're really going towards what is known as progressive decentralization, where some of these properties might not be completely there yet. There might be elements of centralization that over time, by design, are removed, so that we reach a point where these applications or platforms are completely decentralized, with no single entity or single or groups of entity that can really manipulate that platform and abuse it, right? So that is where we are headed towards. Now let's step back and pose the question of why, right? Or really the purpose of Ethereum as a platform, and what is that vision that is being worked towards. Again, there is, because of the decentralization aspect, because of there being not one entity controlling the vision, a lot of this is, think of them as narratives, and this is the purpose that we are going to be talking about. Is really what was put forth in the white paper, which was really the initial vision, and some of this has evolved over the last 7+ years, and it continues to evolve, right? And we'll come back to this. I mean, this is something that is recurring, and we'll touch upon this topic multiple times. But Ethereum, the initial purpose, as set forth in the white paper, was for it not to be just a currency, right? And not for it to be just a payment network. And this becomes if you know this becomes clearer if you're aware of how Bitcoin works, right? Bitcoin is a predecessor of Ethereum. Large source of inspiration for Ethereum came from Bitcoin, and we'll talk more about that. But compared to Bitcoin, Ethereum, uh, the vision was to go beyond it being a currency or a payment network, right? Um, there is a native currency of Ether that is required on Ethereum for for really operating any part of the infrastructure for interacting with it. It's necessary and integral to Ethereum, but it's not really the be all or end all goal of Ethereum, right? The idea for Ether was for it to be a utility token, right? You need Ether, the Ether token, to utilize the benefits of the Ethereum platform. So if somebody wants to use Ethereum, they need to pay using Ether. So this is the high level purpose. And if you've been around this space, you've been reading about Ethereum, you'll see that there are narratives of Ethereum or Ether being store of value, medium of exchange, or a digital gold, or a world computer, productive assets, things like that, right? So these are all the narratives that are being discussed in the community, that people think of Ethereum or Ether in different ways, and we see its usage along all these narratives, and some of it is changing as well, right? Something to pay attention to. So how does Ethereum, and specifically the programming language in Ethereum, how does it compare to what's available on Bitcoin? So Bitcoin has what is known as a Bitcoin script. It is a scripting language. It's intentionally by design limited. Script really allows uh, uh, evaluation of spending conditions that evaluate to true or false, and that's really what is required for Bitcoin and what it's supposed to do. But when you look at Ethereum, Ethereum supports a virtual machine known as EVM, Ethereum Virtual Machine, and by design, it is meant to be a general purpose programming language. It's Turing complete. We talked about this, which means it allows smart contracts written on Ethereum to be, not bounded by the expressiveness of the language. So the smart contracts can be arbitrary in nature. They can encode arbitrary state. They can encode arbitrary rules, and they can be unbounded in their complexity and expressiveness. So that is a key differentiating feature of Ethereum's power, expressiveness when compared to Bitcoin. Now, how does Ethereum compare to Bitcoin as a blockchain? Bitcoin as a blockchain, like I said, is a predecessor. Right? It came about in 2008, 2009, and by design, the Bitcoin blockchain really, focuses on the ownership of Bitcoins. It's really the ownership of these coins that the consensus of the blockchain is trying to look at, and nothing else, right? So all these state transitions uh, really track the transfer of Bitcoins. And in the case of Bitcoins, they're referred to as UTXOs, unspent transaction outputs. And that is what the entire blockchain, all the operations, all the states, the state transitions really focus on. Compared to that, the Ethereum blockchain is working on, or is focusing on by design, general purpose state, right? State that does not only focus on the ownership of Ether, but anything that can be encoded with the EVM general purpose programming language, right? So we are really, with Ethereum, looking at general purpose blockchain that can encode arbitrary state and arbitrary rules for the transition. So we're looking at tracking not only the state of currency ownership of Ether on the platform, but the state of the different smart contracts as transactions interact with them, right? So that is the key difference between Ethereum and Bitcoin, right? So Bitcoin is UTXO based and Ethereum is state based or account based. And we'll see more of, we'll dive deeper into each of these concepts, but that is the high level takeaway, when it comes to comparing Ethereum with Bitcoin, both as a blockchain or, the scripting, the expressiveness aspect of the programming language. Now let's look at what are the core components of Ethereum. The underlying network that drives Ethereum or that Ethereum is built on is a peer-to-peer network that's running on today running on a TCP port 30303, and the protocol that enables this P2P network is known as Dev P2P, right? So if you step back and think about the networks that we use today, we still use the entire stack, the TCP/IP stack, but the paradigm that we're used to is really built around this concept of clients and servers. The laptops, desktops, the smartphones, the IoT gadgets that we use are all really the clients that are talking to servers sitting in the cloud on AWS or any of the application platforms that you're interacting with, right? So compared to that, the key change when it comes to Ethereum is that the underlying network is all peer-to-peer. There are no clients and servers. They're all peers that are exchanging messages at that layer. And we'll talk a bit more about this in the coming slides. And on this network, we have transactions that have this notion of a sender, a receiving entity, a recipient, transferring some value and transferring some data. And on top of that, there is this abstraction of a state machine that is driven by the Ethereum virtual machine, really everything runs on that machine. And when it comes to programming that machine, there are high-level languages, HLLs, that that programmers and developers work with. And the most common one is, most widely used one is Solidity. And this is something we'll dive much deeper into in the bootcamp. But this is what developers work with. They program with the Solidity programming language, and that is converted into EVM instructions, machine code, machine language instructions, and that machine language instructions is referred to as bytecode. Right? We'll look more into each of these, but these are some of the high-level core components that power Ethereum. And when you look at what data structures are used within Ethereum, there are many data structures used for those coming from a CS background. You have arrays, you have lists, you have the basic value types, you have reference types, and in the case of this is all within Solidity. But then if you look at Ethereum, if you look at the data structures that are used within the Ethereum protocol itself, there are many of the common ones, but then there is one specific or special data structure known as the Merkle-Patricia tree that is used to to optimize the way that Ethereum handles some of the state that is used within the context of the blockchain, right? And we'll touch upon some of these later again, but these are some of the high-level core components used within the Ethereum blockchain. And there are more core components, right? One of the critical ones, perhaps the most critical one, is the consensus algorithm. Why do we need this? If you see how a blockchain works, there are many nodes within a blockchain, right? And these are all peer-to-peer nodes. They're all talking to each other, and they're trying to agree upon what is the global state. Each of them has a local state. The transactions that come in, the blocks that are trying to be formed with those transactions. That's a local state, but then everyone on the Ethereum blockchain should agree upon what is the one canonical blockchain that will be used, in future. So this is agreed upon by what is known as a consensus algorithm. And in the case of Ethereum, the consensus algorithm used is the Nakamoto consensus, and this is the same one that is used by Bitcoin as well, and it's based upon the proof, what is known as a proof of work, POW. And proof of work is, we'll dive more into this, but proof of work is really used to determine which entity on the Ethereum blockchain gets to add the next block. And this is really used as a form of Sybil resistance. If you're not familiar with that, please look it up. We'll share some references as well. But the proof of work is really what drives the Nakamoto consensus, and the consensus algorithm determines which is the longest chain so far, and all the nodes or the node that is chosen to add the next block to the existing canonical blockchain really adds that to the existing longest chain and builds upon that. Right. So this is this is how a blockchain grows in state. A new block is added, and we'll see a bit more about that in some of the details in the forthcoming slides as well. So proof of work driven Nakamoto consensus. And if you're following what's happening with Ethereum and maybe even some of the other blockchains, the proof of work aspect is being replaced by what is known as proof of stake, POS. And this is with Ethereum, it's happening with the transition to Ethereum 2.0 or Serenity, as we've been calling it. So this transition is already underway, and many of these changes are happening as we speak, and proof of work is going to be soon replaced. I think by the end of this year is the target, with the proof of stake. So fundamental changes to the Ethereum protocol happening as we speak. And why is this important? From a security perspective, this is something critical to the economic security of a blockchain. Right? What makes the blockchain resistant to attacks from any of the untrusted parties operating the infrastructure or operating on it? So that's the crypto economic security aspect, and proof of work is really what provides that economic security. And there's this concept of 51% attack. So look it up if you aren't aware of what that is. If 51% of the participating entities collude, then they can actually go back and change the state and the transitions that have been encoded into the blockchain in the past. And this breaks the key property of immutability of a blockchain. Right. So this is very critical. Maybe we won't talk more about the economic security because it's really focused. I mean, the bootcamp is really focused on smart contract security. But I would really encourage you all to look at this aspect if you're not aware already, because this is something very fundamental to the security of Ethereum and really any blockchain out there. So the protocol itself the consensus algorithms, data structures, all these core components are implemented within what are known as Ethereum clients, right? I mean, if anyone is running an Ethereum node, they're really using one of these Ethereum clients that have been built by multiple teams around the world. And the most popular ones are the ones listed here: Geth, Aragon, Nethermind, Open Ethereum, and a few others as well. So there have been a lot of transitions and changes. Some of the clients have been under development, and some of them are way more popular. Geth, I think, is the most popular, with more than 80% of the running nodes using Geth. But then with the design goal or motivation of diversity, other clients are being supported as well and being developed as well. So this is very, very critical to the diversity and the decentralization of Ethereum. So I would encourage you to take a look if you're interested in this aspect. Dive into it. All these clients are open source, so you can really go and examine the client code and maybe even contribute to it. So that's something that's very interesting. Now let's talk a bit about halting problem. So we talked about Turing completeness and how Ethereum supports a Turing complete programming language. And this is fantastic, but then it also lends itself to a fundamental problem in computer science, something that's goes decades back in the computer science literature, and that was actually put forth by Alan Turing, is this aspect of halting problem, right? So if you have a CS background, then you're probably aware of this. But otherwise, look it up. This is very fundamental to how computing works. Fundamental to how programming languages are designed. We just take it for granted, but something that's very critical. What we talked about what Turing completeness is, right? Arbitrary complexity, unbounded expressiveness, but if you have a programming language that supports Turing completeness, then an arbitrary program in that language with an arbitrary input, if we are given that combination, then what the halting problem says is that we cannot predict if that program will stop for that input. Now you can imagine why that is important, right? I mean, we take it for granted. So, on our laptops or wherever on our phones, if there are programs that sort of run into an infinite loop that hang, then we just go and kill it. That's okay. But in the context of a blockchain, we're really talking about being able to deploy a smart contract that is not going to run on my laptop, only on my machine or my Ethereum node, but is really going to run on all the Ethereum nodes in the blockchain. Now, with that in mind, if any of those smart contracts can really run forever, right? Run into an infinite loop, then that whole infrastructure comes to a grinding halt. So that is obviously undesirable. I mean, it's a fundamental thing. We would not make forward progress, and everything would come to a standstill, right? So, that is that is the concept of a halting problem that applies to Turing complete platforms, including Ethereum, right? So in the context of a smart contract, we won't be able to predict how long will that smart contract run, and will it even stop, or will it keep running forever? And the way that Ethereum deals with this aspect is by constraining the resources that are given to the smart contract on the Ethereum node. And the way it is done is by metering using this concept of gas. And this is something that's again critical, and let's take a look at what that means. Gas metering. So the EVM runs smart contracts. Smart contracts have machine code instructions. The EVM instructions are byte code. Every one of those instructions, each instruction in the smart contract has a predetermined cost in gas units. So when a transaction triggers the execution of that smart contract and the smart contract starts executing those instructions, then the gas units for those instructions are consumed by the smart contract. So this is the concept of metering within a smart contract, where it accounts for every instruction, and that could be a computational instruction, it could be a data access. All those instructions consume gas units from the transaction, which means that a transaction that triggers a smart contract has to include a specific amount of gas as required by the logic of the smart contract. And depending on what logic needs to execute, there is a limit to the gas. So a certain amount of gas units are required for a particular flow. So if a transaction is triggering that, it must include so many gas units. And if the gas that is required during the execution of the smart contract, if it exceeds what is supplied, or if it exceeds the limit, then the EVM will terminate execution at that point and the transaction will fail. Right? So this is fundamental to how Ethereum works. If you haven't interacted with any of the Ethereum applications, then I would encourage you to understand a bit more, because this is something that we do not see in Web 2. In our existing infrastructures, we really don't have this concept of gas. Where when you open a website or do anything else, open an app, this is not there. So this concept is critical to how Ethereum, how blockchains work, because of really the way that blockchains are designed, because of incentivization, because of the economic security aspects, and because of, in this case, because of Turing completeness. There needs to be a way to bound the use of resources by anyone interacting with a smart contract that runs on all the blockchain nodes all over the world, right? And this is how Ethereum allows the use of a Turing-complete programming language, is by constraining or bounding the amount of resources that can be consumed by limiting the amount of gas that is required for that transaction. Now let's get into some of the details of the gas mechanism. How does that work? So like we said, a transaction has to supply the gas depending on what action it is triggering. It might be interacting with a smart contract, or it might just be doing a transfer of value. In any case, it has to supply the amount of gas that is required. Now that's the units of gas, but the price of gas is measured in Ether, the native currency, right? And the gas price itself is not fixed. It depends on the supply and demand. It really, in this context, it depends on the demand for the block space within Ethereum. And if there are many applications, many smart contracts, many users competing for that block space, then the gas price can go really, really high. And we'll talk a bit more about the gas mechanics of how this gas price is set, who sets it a little later, but it's not fixed. So the key point here is that there is there is a concept of the gas units, and then each unit has a certain gas price which is not fixed. And the analogy that is commonly used is that of an automobile, which requires gas or petrol. So you put in the gas or the petrol, you put in, let's say, a liter or a gallon, and with that you're able to drive so many kilometers or miles. So that is the equivalent of the gas units in Ethereum, which allows you to run a transaction, a certain number of instructions within the smart contract based on the amount of gas you supply. But the gas price, similar to the price that you pay for gas in gas stations, petrol bunks, is different. Depends on the supply and demand and other aspects of the supply chain. Similarly, in the case of Ethereum, we pay a different gas price, right? And it really depends on supply and demand. So that's the takeaway here. So take a look at this, spend some more time. This can be confusing initially, this concept of gas units, gas price, but it's really critical to how Ethereum works. And as we speak, I know some of these, there are some changes to how the gas mechanism works in Ethereum that is being that's being put forth, or that have actually been put forth in the past few months. So if you have taken a look at EIP 1559, it changes the way gas works within Ethereum, right? So that's again out of scope for the level of depth that we want to cover here, but I would encourage you to take a look at it and understand it a bit more if you're interested. So gas, one needs to purchase gas, right? And this is purchased really by purchasing Ether, the native currency in which the gas price is measured on Ethereum. And a transaction requires gas, and if it exceeds exceeds the amount of gas consumed during the transaction exceeds the amount of gas that is supplied, then the transaction fails. But if there is more gas than what is required that is supplied as part of the transaction, then the remaining gas is sent back as part of the protocol, sent back to the sender who executed the transaction. Right. So this is really fascinating. It's really what underpins how Ethereum works. So feel free to take a deeper look at this. DApp, Decentralized Application, or DApp as it is abbreviated. This is something that you will come across often whenever you build any application on Ethereum or on a blockchain. You're building it on a decentralized infrastructure, so the application is really fundamentally different from the mobile applications or the desktop applications that we are used to today. So these are referred to popularly as decentralized application. They really combine a web app or a web front end running on a peer-to-peer infrastructure. And the peer-to-peer infrastructure is a combination of compute, storage, and network. In many cases, we have one or more of the at least one of this, or one or more of this, right? So in the case of Ethereum, it really is the compute part. So we'll be using the P2P compute aspect over there, and there are peer-to-peer storage aspects such as IPFS and some of the other protocols that we won't talk about, but that is really the underlying peer-to-peer infrastructure that lends itself, or that powers, a decentralized app, right? A DApp. But at a high level, the DApp that we interact with is really made up of two components. We have a web app, or maybe a mobile app front end that really interacts with a smart contract on the Ethereum blockchain. Now let's step back, go a little higher to see what is Web 2.0 and how does that compare with the Web 3.0 that we are building with Ethereum. The property that really underlies what is commonly known as Web 2.0 is this concept of a client-server paradigm. We talked about it earlier. We are used to using cloud services that have servers running on the cloud where we interact using our clients, be the laptops or the phones or the smartwatches, that is today's infrastructure, right? And if you're interested in the history of the web, the internet, if you go back 40, 50 years, you will see that it started out as Web 1.0 with some of the browsers and some of the initial protocols, the file transfer or the telnet protocols, things like that. And then the web, the World Wide Web, was built on top of it. And that was really Web 1.0. Or at least it's popularly referred to as Web 1.0. And then over time, in the last 2 decades or so, the infrastructure, the entities building the web and the infrastructure have changed. We have huge corporates, the Googles, the Facebooks, the Amazons of the world that are building this infrastructure. So that is popularly referred to as Web 2.0, right? And one of the key properties or aspects of Web 2.0 is the fact that they're centrally managed. You have all these corporate entities that determine what the infrastructure is, what the products are, what the next versions of the products are, and those are rolled out. And we, the consumers, use all these applications that are rolled out, right? But there's still the users really do not have a say in how the infrastructure is managed or what the applications evolve, or in sometimes don't even have a say as to what kinds of applications can be deployed on it. The censorship aspect that we touched upon earlier. So that's really one of the key defining aspects of Web 2.0. And when you look at the economic aspects of Web 2.0, the business models are really built around freemium models where the basic application is free, but then you want to upgrade, you have to pay up, right? So that's the premium, the free plus premium aspect or the freemium aspect. But a lot of the business models, if you look at Google and Facebook especially, they're built around advertising, right? Where the product is really free, the user is the product, and the interactions, the data that the user shares with those platforms is really monetized in the form of advertisements, right? That are being delivered to the user. So this is something that we've just got used to. We don't even really pay attention to. We have been in some way desensitized to these business models that has been talked about. I mean, the negative aspects of it, the negative impacts have been talked about, right? So this is something that Web 3.0 is trying to get away from, right? It's trying to go back to the original vision of the web, which was to, for it to be completely decentralized, completely peer-to-peer, where there are no centralized entities that can dictate what can be done on the platform, what can be deployed, or who can use it, all these concepts that we talked about. So that is the vision that Web 3.0 is really driving towards. And this is in compute, it is in storage, it is in network, all these three critical aspects of the infrastructure. So this is really what decentralized Web 3.0, where Ethereum is headed towards. Now, when you look at the business models, if everything is decentralized and there has to be some incentive for users to deploy the nodes, for users to actually contribute to the development of the code, to development of the clients, development of the smart contracts, applications. So this is driven by what is known as incentivized participation, right? So this goes back to the concept of crypto economics. Now, this is, I would encourage you to look more into this. This is fascinating, which is really what drives the vision of Ethereum and Web 3.0 in general. It has big implications to how security works, because there is no real centralized entity that can deal, manage, and do instant response. All these aspects of security really fundamentally change because of these underlying principles of Web 3.0 and Ethereum. Now, in the case of Ethereum, what is the peer-to-peer infrastructure that drives the underlying framework, right? So in the case of Ethereum, the compute aspect is really Ethereum itself. Ethereum as a blockchain, it's really used for decentralized compute. For storage, there is Swarm, and for network, there is Whisper, which is now evolved into Waku, right? So this is really the triad, or the three critical components of compute, storage, and network that power Ethereum as a decentralized infrastructure. Now we keep talking, we've talked a lot about decentralization. It's a very loaded word, very heavy word. Now what does it really mean, right? This is something that we use it very casually, but we really don't pay attention to, and has big implications to how we think about security, even for smart contracts, right? So let's take a little more look into what this means. There are various definitions, various sort of ways, narratives about decentralization, but the one that I like is the one put forth by Vitalik in his article on decentralization. So this is this is there in the references. I would encourage you to take a look at it, try to understand it. But what it really talks about is the notion of there being three types of decentralization. There is architectural decentralization, and this really refers to the hardware, the physical computers, right? Who runs them, who owns them, who is managing them, who can start them and stop them. So is this being done in a decentralized fashion or not, right? The next one, which is again very critical but often missed, is the concept of political decentralization. This refers to the people behind the hardware, right? Or what is commonly referred to as wetware, the humans behind it. Who are the individuals, who are the organizations who control the hardware, or the infrastructure as such? Is it just one individual, or is it a group of individuals who are colluding, or are they independent and decentralized in that fashion? This again has big implications to security, and we'll look more into this. So there's architectural decentralization, there is political, and the third one is what is known as logical decentralization. This refers to the software aspects, the data structures that are used in the software, that are used to build out the application, be it the framework itself, be it Ethereum, the code, the protocol itself, the data structures in it, or the smart contracts or any other software that runs in that stack. Is that decentralized? Is it one monolithic entity that cannot be split apart and used in a decentralized fashion, or can it be done so, right? So these are three very interesting ways to think about decentralization when it comes to Ethereum or anything that is built on top of Ethereum and has security implications, like I said. Let's take a deeper look at the native currency. And this is Ether, as we talked about. Now, Ether is, it's not indivisible. It is actually divisible, and divisible up to 18 decimals, right? This is again something that you would come across, when you're looking at smart contracts. The fact that if it is managing Ether, then you will see this notion of managing the divisible units of Ether. And the smallest unit of Ether is known as Wei, right? And this is the fundamental unit, which means that 10 power 18 Wei add up to 1 Ether, right? And this comes from the fact that Ether has 18 decimals, so that's the math behind it. Now there are other units as well. There is a Babbage, 10 power 3 or 10,000 Wei adds up to or is referred to as a Babbage. And 10 power 6 Wei is known as loveless. Now, for those who are familiar with some of the history of computer science, computing, you'll see that these names come from Charles Babbage, Ada Lovelace, and in the case of Wei, it's Wei Dai, and all these are names of really famous people who contributed a lot to computing, to cryptography. So that's some of the math behind the native currency of Ether. Now let's shift gears and take a look at the cryptography that powers Ethereum. If you have a CS background, and if you have taken or looked at cryptography, then you're probably aware of two classes of cryptography. There is symmetric cryptography and there is asymmetric cryptography. Asymmetric cryptography is also known as public key cryptography, and that is what is used within the Ethereum protocol, and that's what we'll be talking about. So it's public key cryptography because unlike symmetric key cryptography where there's a single key, here we have two keys. We have a key pair. There's a public key component and there is a private key component. The private key, by definition, is a secret, right? It has to be kept as a secret. It has to be kept private, and this can be used to derive the public key. And the public key, by definition, or as it is worded, is public by nature. So this is something that can be shared publicly. It doesn't have to be a secret. It is used by others to engage in cryptographic protocols with the owner of the private key. And in the case of Ethereum, the cryptography that is used is really all or mostly about digital signatures and not really as much encryption at a protocol level, right? So digital signatures is something that is fundamental to how Ethereum works, and it's powered by public key cryptography. So that's the takeaway from the slide. So I would encourage you, for those who are interested in the math or the cryptographic aspects, to look deeper into this. And if you aren't aware, try to get a grasp of some of the fundamental concepts of cryptography, because that's really critical to how the protocol works. Some of the many of the concepts in security of smart contracts really depend on this. So this is really fundamental, and it's critical that you understand it correctly. The digital signature algorithm used by Ethereum is the same one that is used by Bitcoin as well. It's known as ECDCA, elliptic curve digital signature algorithm. Now, elliptic curve cryptography is it's an approach to public key cryptography, and it's based on a particular algebraic structure of elliptic curves over finite fields. And if you're interested in the cryptographic aspects, the theory, please feel free. I mean, these are fundamental primitives that have been around for a long time, time-tested, used in multiple domains, and Ethereum and other blockchains are built using these fundamental primitives. And in the case of Ethereum, the particular elliptic curve that is used is known as SecP 256K1. This really refers to the parameters that are used for the elliptic curve, and this is again the same curve that is used by Bitcoin as well. Right? So elliptic curves over finite fields drive the underlying cryptography, the public key cryptography used by Ethereum. That's really fundamental to how digital signatures work within Ethereum. Right? Now let's touch upon some of the basic concepts of keys, accounts, and such that are fundamental to understanding how Ethereum works. Private key, like I said, it's meant to be a private in nature. It is a secret. It has to be guarded as such. In this case, it's a 256-bit private key, and it's a random number. It's effectively a random number, and it's used to derive the public key, and the public key in turn is used to derive the address of an Ethereum account, right? So this is sort of the high level aspect that you need to remember. There's a private key, there's a public key that is derived from it, and from the public key we derive the address of the Ethereum account. And we'll see a bit more about this in the coming slides.